In this video, I want to look at solving a separable differential equation using logistic modeling. So logistic modeling is one of where we have the rate of change is equal to, let's say, some constant k multiplied by a population m minus the y variable times y. Now, in some cases, we might use the terminology such that we want to basically say that m represents a population, k is a constant, growth constant, and the y is the function that we're looking for, which in this case will equal to the function that we describe as y equals f of x. Now, in any case, y equals f of x is usually some kind of function that describes, say, for example, like a logistic function of which would be modeling a influenza or some type of disease that is spreading at this particular rate. So the question would be really, though, how do you solve, for example, an equation like this? And the idea is the separation of the variables. So you would take basically that dy would be divided by m minus y, and you have y, but this equals the k, and this is dx. The next step that you would do is that you would basically just integrate on both sides, of which this would be just basically kx plus c. But then from here, it becomes a question as to how do you solve the left-hand side, that is. So, for example, if we have 1 over m minus y, and this is times y, using partial fraction decomposition, we could write this as a over m minus y plus b over y. Now, in any case, we could solve this via either cover-up method, or we could just use that if you multiply by the LCD, you have that 1 equals to a times y plus b times m minus y. Now, of course, if you plug in that y equals to m, then basically you're going to get that a equals to 1 divided by m. That's interesting. M, so 1 over m. But if you plug in 0 for y, you would similarly get the exact same thing, that b is equal to, basically you have the 1 over m. Okay, now, in any case, though, we see that basically what happens here is that you have that this becomes 1 over m, and this is going to be 1 over m minus y, and this is going to be plus b. Not b, but 1 over m. And that's 1 over y. Now, from here, you have that you could technically just rewrite this as 1 over m, and then basically you have the 1 over m minus y plus 1 over y. Now, from there, what you can do is integrate so that we can get the left-hand side, that is. So we have that basically that you're just going to have 1 over m, and then the integral of 1 over m minus y plus 1 over y, and then from there you have that equals to 1 over m multiplied by, well, the integral of this would be negative the natural log of m minus y, and this would be plus ln of y. And then from there, though, now we can go back and say, well, we have that basically if we have this is 1 over m is going to be multiplied by our negative ln of m minus y, and this is plus the ln of y, and this is equal to, well, we said that that would be kx plus c. So if we multiply by, let's say, like, conveniently by negative m on both sides, well, this is going to be the natural log of m minus y minus the natural log of y equals to negative mkx. But this is plus c, though, right? Okay, now the next step is that basically you would need to essentially take that this becomes the natural log of m minus y, all divided by the y variable, and this equals to, as we said, negative mkx plus c. Now, the next step which comes is that if you say that, for example, that you take the e on both sides, or you raise both to the e, that you end up with the following. M minus y is divided by y, and this equals to, well, note that in any case you would have e to the c. So you would have e to the c multiplied by e to the negative mk x in either case. But nonetheless, this is a constant, this e to the c. So that means that you could technically just rewrite it as an arbitrary constant. So we have that this would be c times e to the x. Now, what comes next is that, for instance, if we said that the population had that there was an initial amount that would be, suppose, sick, infected, or what have you, then we would say that initially at 0 that you're going to have y sub 0. Now, what that would imply is that when you plug in 0, of course, you're going to have that this is going to give you that m minus y of 0 is divided by y of 0, and this is equal to your constant, because you have that this is e to the 0, which is just 1. So basically your constant is going to be m minus y0 divided by y0. So in any case, though, that means that basically it's kind of like you have this very large constant in either case hanging around. But if you prefer, what we could do before we do that is just say that, well, m minus y equals to basically, well, in this case, you have y times c times e to the negative mkx. But then notice this, that you could just solve for y by just taking m and setting it equal to y. But notice that in this case, you're going to have y times c e to the negative mkx, and this is plus the 1 times y, so that's just 1. And then in any case, now we are almost done, because we can solve for y. How? We just divide out this whole part in the parentheses. So what that does is it gives you that y of x is equal to this population m divided by 1 plus c, and then we have e to the negative m kx. Now, in any case, though, you would technically need to substitute the c value into this part right here, which in any case, if you were going to do that, you would have y of x is equal to m, and this is divided by 1 plus, so we're taking the population, and we are telling ourselves that you're going to subtract the initial, you're dividing by the initial, and then you have e to the negative mkt. Now, in either case, something like this would actually give us precisely the logistic function. And this is a logistic function right here, of which it satisfies that initial differential equation that we actually came up with. So from there, though, like if you needed to find the point of inflection, you could take the first derivative and then find the second derivative, but it would be a lot easier to just work off of the rate of change, how we know that the rate of change is k times m minus y times y, which in either case, if you take this as distributing the y minus y squared, how do you find a point of inflection? You take the second derivative, of which in this case, this would give you k times m minus 2y. But then how do you find that it's a point of inflection? You set it to 0, which would basically tell you that y equals to m divided by 2. So that tells you that the point of inflection would occur at precisely when half of a population has been reached, that is. So if we were to use a practical application to this, we could probably utilize that what if you had a population of 50,000 people, and then what if initially you had that there was 100 people that had some kind of illness or sickness, that is, but then you have that after, let's say when x is in days, so that's going to be days, then you could say that, for instance, maybe after 7 days, that 470 people became sick. So in any case, if you were to put this all together, you would basically have that the equation would be y equals to 50,000 divided by 1 plus. Now, in any case, 50,000 minus 100 divided by 100 is going to be 499, and this is going to be e to the negative 50,000, and that's going to be kt. Now, if you're trying to figure out, for example, like what is the constant k, note that you don't need to find the constant k because you still have to multiply by negative 50,000 technically. So with that, you would basically just say, what if you just set this equal to, like in this case, 470. So you have 470 equals to 50,000 divided by, and let's say that this is going to be 1 plus 499, and this is going to be e to the, let's say, 7 n, where n is equal to the negative 50,000 k. Okay. So in this case, this would mean that you would just technically need to cross multiply and then just solve algebraically in either case. So that can be done by just saying that, okay, well, in either case, how do you solve this then? You take the 50,000 because you have to cross multiply basically. Or you could just say, okay, well, why don't we just do the proportionalities? That way might work too. So, for example, like if you do the cross multiplication, you have 1 plus 499, equals to, well, 499 e to the 7n, right? And this is equal to 50,000, and this is divided by 470, okay? So in this case, though, how do you solve for the constant that we're calling n? Well, in any case, what we're saying is that you just have to subtract 1 and divide by 499. So you get e to the 7n equals to 50,000 divided by 470 minus 1. But remember that we have to divide this whole thing by 499. But notice this. What do you need to do with this? You need to take the natural log of it. So once you take the natural log on both sides, you have that the solution is going to be n equals to, well, you have the natural log of 50,000 divided by 470 minus 1, but all of this was divided by 499. And then from there, you have that all of this has to be divided by 7. Keep in mind that, ln of 7 to the n is just 7n. So in that case, we have that, you have the n value, that is. So if we go and we do this, we can actually just say, well, 50,000 divided by 470 minus 1, and then divide that by 499. But keep in mind that you have to take the natural log of this, so natural log. But then what do you do after this? You divide by 7. So this is our constant in this case, because we're saying that n is equal to negative 0.2221, for example. So this equals to negative 0.222 and maybe 1/4, right? So what that means is that you can now substitute the value that we have, because we have that this represents the value of the negative 50,000 K. Okay, so in this case, we have that basically, we can then state our function. And let me just put it over here, where we'll just say that, well, okay, so we found that y of x is equal to 50,000 divided by 1 plus 499, and that's going to be e to the negative 0.22214, and then we said x, right? Now, in this case, though, if you wanted to basically figure out the value of which that would give you that this is equal to 25,000, you would essentially do more or less the exact same thing, where you would say that you have 50,000 is divided by 1 plus 499 e to the negative 0.22214x, and basically you would say that this is equal to 25,000. Okay. Now, using a little bit of cross multiplication, you would figure out that basically that 50,000 divided by 25,000 is basically 2. But that's equal to 1 plus the 499 e to the negative 0.22214 x, right? So when you solve for e, you're basically going to get that e is negative 0.2214 x equals to, well, 1 over 499. Okay, so from there, you can see that essentially all that you would need to do to solve for x is just take the natural log similarly. So you have natural log of 1 over 499, and this is all divided by negative 0.22214. So in this case, we have 1 divided by 499, and we're going to divide this by 0.22214, and that's a negative. Actually, is it 1 divided by 499? And then natural log. Okay, there we go. So that's negative 6, sorry, divided by 0.22214, but it's negative, and we hit enter, and, well, it looks that basically for this, we have that this is approximately 28 days, which means that the population in this case would be at 28 days, it would be half of the population, which in this case would be sick. Now consider this, like, like if you did graph this in your calculator, well, I mean, if you do like a, like if you get like a rough sketch of it, you're gonna see that it kind of looks something like this, of which in any case you have this point of inflection is at 28 days, which in this case, you kind of think about it, what could be done in just 28 days? 28 days allows you to actually plan for that peak of which would occur for this particular, virus or sickness and so on. But then again, like for instance, like this constant that we have right here, what if we could lower that? Then in that case, it's like we're prolonging this disease or sickness such that we have that the peak would not occur at 28 days, but perhaps like 40 days, etc. But then again, like if we have that, it just worsens, like if we have that it's moving at a faster rate, then maybe this would happen a lot sooner in actuality, and we wouldn't want that. And in either case, the whole goal for this is that we actually would flatten the curve, if you will. So this is just one way of which that we can use a separation of variables related to logistic models and how they describe basically, like how a, in this case, like a sickness or a virus or disease is spreading if it's such that the rate of change is directly proportional to the number that was present, that is. Now keep in mind that in actuality, though, the nice thing about having that rate of change is that now that you have the rate of change, you have that basically the k. Well, the k is basically the 0.22214 divided by the 50,000. And then you have that this was 50,000 minus the y variable times the y. Now, how does this help you? Well, in any case, it would allow you to determine such that, how fast is this virus spreading, for instance, at 28 days? Well, you could probably just say take 0.22214, divide this by 50,000, and you would multiply that by how many are exactly sick, so that's half, so times 25,000. But then you multiply this by another 25,000 basically. So this is telling you that basically the spread of this particular virus is spreading at a rate of 2,777 people per day. So note that it went from, 100 initially. Like if you plugged in 100, you could actually figure out similarly, like what was that to begin with. But let me just write that down because I have that basically that, yeah, that I figured out that it's spreading at a rate of 2,777 infections, and that's, per day, if you will. Um, but then, like if you compared it to, let's say, like for example, the initial, you had 100. So like, okay, that computation can be found. How? By taking, let's do it like this. Let's do 50,000 minus, okay, so how many were sick? 100. And then it's multiplied by the number that are sick. So it's multiplied by 100 also. And then this is multiplied by the 0.22214, and then this is divided by the 50,000. So it's saying that it spreads at a rate of near 23 people per day. So we went from 23 people per day to 2,777, nearly 3,000. In 28 days, actually. And then similarly, you could see, like, how fast is it spreading at 14 days, that is, in either case. So we see that basically in knowing the equation that we have for the rate of change, it allows us to not really deal with this equation in terms of, like, finding the derivative, plugging in the value of x, finding the second derivative, and that kind of stuff. So in just knowing, kind of like the data, if you will, we are able to deduce several things about this particular sickness, influenza, or disease, that is, in either case. And, more or less, this is just hypothetical, and it is just more or less a way of planning because, we see that, okay, yeah, after 28 days, that's when this virus has reached its peak. But on the silver lining of this situation is that after the 28 days, we would expect that this rate of change would begin to decrease in either case, which is, yeah, that is going to be better actually. But, you probably want it to not reach that point, and that's the whole purpose of, oh, okay, we have 28 days until basically half of our population has been, affected by this virus, influenza, or disease, that is.